In this video, we will talk about how to construct a direct proof, and we'll do our first ever example of a proof in our class. So the example we'll prove is proving that the sum of an odd integer and an even integer is odd. So to do that, we need some notion of what does it mean for an integer to be odd and even. So our informal definitions of these terms are an integer is even if it is twice an integer. So if I look at some examples, something like 6 is twice or 2 times 3. 2 times the integer is 3. Or 14 is 2 times the integer 7, or twice the integer 7. An integer is odd if it is not even. So while these informal definitions are nice, they're not always helpful to work with in a formal proof because I don't have something concrete like an equation that I can add or multiply with something else. And this is where the formal definitions come in. We say that an integer n is even if there exists an integer k, that's what this is saying, such that n equals, and it needs to have a form like this, n will be equal to 2 times k, 2 times some integer. All right, and an integer n is odd if, let's see if we can do something similar for odd integers. As an example, well, 15, notice that that's 2 times 7, which is 14, plus 1. Or 9 is 2 times 4 plus 1. So an odd integer is always going to be 1 more than the even integer that's right below it. Okay, so the way I write that is my integer n is odd if there exists a k in the integers such that n equals 2k plus 1. Okay, and these are nice to work with because these are equations. Very nice to do algebra with these. All right, so to our proof. I'm trying to prove the sum of an odd integer and an even integer is odd. So first, let's restate this a bit more formally. We're trying to show for all integers x and y, if x is odd and y is even, then x plus y is odd. So one thing I want to be very careful about, because we have a for all statement, it's not enough to just give one example where it works. For example, if I were to say x is 3 and y is 8, in which case adding them together we get 11, and that's odd, well, that's not sufficient to prove this statement because we've only shown that it works for this one example. But we're trying to show that it works for all possible odd x values and all possible even values. So the strategy that we'll use to do this is, if I'm trying to show something is true for all whatever, odd integers or even integers, we're going to try to show that it's true for an arbitrary odd integer or arbitrary even integer. And what that'll mean is we're going to keep considering, we're just going to assign a variable to this odd thing and a variable to the even thing, and just work with that variable, and well, that will show it's true for any choice of x and any choice of y. Okay, so let's get to the proof. So before I actually prove this thing, I want to first do some scratch work. And in the scratch work is where I play around with the problem, and I'll first write down what it is that I'm given, that I know, / what it is that I get to assume, what are my assumptions, the things that we get to assume are true, and what it is that I want to show. So the things that are given to me are, well, it tells me that x and y are integers. It also tells me that if in my if-then statement, I get to assume that the if part is given, that it is true. I get to assume that that's true and then show that the conclusion has to happen as a result. So my if part tells me, well, x is odd. It also tells me that y is even. And what I want to show is x plus y is odd. Okay, got a starting point. Now we play around with it a little. Because x is odd, that tells me that x can be written in the form 2k plus 1, where k is an integer. Since y is even, I can write y in the form 2 times And I don't want to use k again because then I'd be assuming it's the same k for both of these, which may not necessarily be true. So I'll use a different variable. I'll use j to denote my integer, which might be different from k. Okay, and eventually what I'm hoping is, can I connect what it is that I'm given and that I know with what it is that I want to show? And I think to do that, I'll probably have to add the x and the y together. If I'm trying to show x plus y is odd, I am trying to show that it has the form 2 times something plus 1, where that something is going to be an integer. Okay, and I think we can get that if we add the x and the y together. So at this point, I think I see a connection and I'm ready for the proof. Okay, so I'm going to separate out the givens from what I want to show, and I'll separate out my scratch work from the actual proof. So again, the scratch work, the purpose of it is just for me to get an idea of how we will do the proof. That's really important before we actually write up the proof in a very clean format. So I begin the proof by writing what it is that I get to assume is true, all the givens. So I'm going to let what is given, x be odd and y be even. So notice how I'm letting x be arbitrary and y be arbitrary. I'm not specifying values for them. Okay, then we say, well, what does that mean? So we use the definitions of odd and even. So this means because x is odd, there exists a k, which is an integer, such that x equals 2k plus 1. And because of y, I get to say there exists, I can't use the same variable. I can't assume the k's are the same, so maybe I'll call it j. J, which is an integer, an element of z, such that y equals 2j. Okay, so that was just me using the definitions and breaking this down. Now is when we do our algebraic manipulations. So I'm going to add the x and the y together. X plus y is, well, x is 2k plus 1, plus the y is 2j. I'm hoping to make that look like this, 2 times an integer plus 1. So I can put the 2k and the 2j together and factor out to get 2 times k plus j, and then plus 1 outside. Okay, and I know this is going to be an integer because k is an integer, j is an integer, and I know that when we add 2 integers, that's an integer. That was one of our axioms of integers. Okay, so what I'm going to do is just assign a new variable to this quantity. So I'm going to notice I'm using full sentences, periods and stuff when applicable. So I'm going to let k plus j be equal to m. And notice that this is an integer. This is an integer because adding 2 integers gives me an integer. Okay, so thus what we get now is that our x plus y equals 2 times m, because k plus j is m, and then plus 1, where the m is an integer. But that's precisely what I wanted to show. X plus y is 2 times an integer plus 1. That's what it means for x plus y to be odd. Nice. So thus, finally, x plus y is odd. We have reached the conclusion. And once we get done with the conclusion, it's commonplace in math proofs to write some sort of symbol to indicate that we're done. A really common one, and the one that I use, is to write a square that's shaded in. Okay, so before I wrap this video, I want to make one important comment about the structure of this proof. And we'll see this structure kind of repeated quite often, especially in the beginning, which is my proof starts off with the assumptions, the things that we get to assume are true, or the givens, the assumptions. And it ends, and the proof ends with the conclusion. Starts with the assumptions, ends with the conclusion. Okay, sandwiched in the steps right after the assumption and before the conclusion were our definitions. We had the definitions right after step 1. And then at the very end, we had the definitions of what would it take to show x plus y is odd to reach that conclusion. And then in the middle, sandwiched in between all of this, the stuff in the middle was our manipulations. In this case, where we did the algebra. This is where the bulk of the work in a proof is going to happen. In this proof, I think it was a bit more straightforward to do the manipulations, but that isn't always going to be the case. Sometimes it's going to take a lot of playing around with the scratch work to figure out what is the connection going to be. And the manipulations can be more challenging to think of. Okay, so that is something that I want us to be ready for. And we're gonna build up our proofs, but just be aware that it takes time to connect these things and to work these things out. So be patient with yourself and persevere during these problems.